Let me now discuss the SPICE simulation of the forward converter. I will open the schematic of the forward converter that I have drawn using GSHM. This is the GSHM schematic, and the forward converter circuit looks like this, just like as we discussed. Look at this portion here, what I am showing through the cursor. The freewheeling action is through the resistor and the diode combination. We are calling this forward converter with lossy core flux reset because after this switch XSW going off, the magnetization energy stored in the core of the transformer will discharge in this path, the freewheeling path, and dissipate in R, and therefore the core flux reset is lossy. So XSW is a generic switch which is used to switch the transformer primary. This is the PWM block which we have used earlier in the non-isolated converters. I've used these voltage source, zero value voltage sources to measure currents. I'm measuring the collector current of the switch using this zero voltage source VIQ. I'm using VID, zero voltage source, to measure the freewheeling current, and I'm using VIS to measure the current in the secondary of the transformer, forward converter transformer. And another component, new component, which probably we are discussing the first time in this course, is this transformer. This is a forward converter transformer. It has a symbol and the model. The model for this transformer is located in EDT01.sub, which I will shortly open and describe. And the symbol can be drawn from the component list. You see this component selection dialog box, and A block, A bond, A comms, A models. These are the set of models which I have provided in the resources. In this, select this A components, A COMPS. There are a list of generic components, and in that there is xformer.sim. Now this is what I have used here. Let me close this dialog box, and also note that I have placed some node points here. A for the input DC, V in, there is S here for the secondary of the transformer, P here at the point of intersection of these diodes and the inductor. This is the output node. This node is Q, which denotes the collector of the generic switch. G is the gate of the switch, all with respect to the circuit ground. So with this kind of the circuit structure, which we have already discussed, and we know the waveforms at all the various points in the circuit, let us try to simulate it. But before we try to simulate it, we will digress a little to understand the model for XFM, which is located in EDT01.sub. So let me open EDT01.sub now. Now when I click on this transformer symbol, double click on that. It's a dialog box which gives details of this transformer which we have used. So you see that it is a sub-circuit. It has a name, sub-circuit name XFMER, Xformer, and some parameters are passed. NP, primary turns 10, secondary turns 20, and C here represents the permeance of the core. Permeance of the core, which I am setting it to 100 microfarads. but in the magnetic sense, permeance is Henry per turn square. So this is the model that has been used. Now let us look at the EDT01.sub. So I'll double click on the EDT01.sub and look at the library of components. So we have diode, default diode, the power diode, switch. So I'll keep going down. This is the PWM block which we saw earlier, and here we have the electromagnetic transformer, and you see it's a subcircuit and it has a subcircuit name XFMER, the same thing that we used. You can see in this dialog box. NP is 0 primary terminals, NS0 secondary terminals, and we are passing some parameters. NP is equal to 10 in this case. What we are passing, NS secondary number of turns and the permeance of the core. And within here it uses two other subcircuit models called gyrator, GY. And two gyrators are used to make this transformer, and a conditional statement here to account for saturation of the permeance. We are having permeance. To account for saturation of the permeance, we are using this model. So what is a gyrator? So let me digress at this point and describe gyrator, then you will be able to understand this model of the electromagnetic transformer. Let us now understand gyrator operation. Let me explain this now. Let me take a block. Let us consider that this is the gyrator. It is a two-port device. There is one input port and there is one output port. Power or energy flows from the input port into the gyrator and out of the gyrator output port. So the input port has two power variables. One will be E1. I will call this as the potential variable, and another is I1, which is the kinetic variable. So in the electrical terms, E1, the potential variable, will represent voltage, and in the electrical domain, the kinetic variable will represent the current flow. Likewise, you will have two power variables on the output side, E2 and I2. E2 represents the potential variable and I2 represents the kinetic variable. And there is a gyrator parameter. Most of the time it's a fixed parameter. We'll call this as N. Now, how are these variables related? So let us have a look at that. In the case of the gyrator, the relationship is the potential variable of one port will get linked to the kinetic variable of the other port. The potential variable of the output port will get linked to the kinetic variable of the input port. So this is how the basic relationship, constitutive relationship of a gyrator is. So if we look at the potential variable E1 and the variable I2, that is the output kinetic variable, the relationship is in this fashion. And these two, E2 and I1, are related. So E2 is related with I1 with using this parameter N. So it is N into the parameter I1. So E2 is related to E2, the potential variable of the output port is related to the kinetic variable of the primary port, scaled by the parameter N. Likewise, the E1 is related to I2. E1, the potential variable of the input port is related to the kinetic variable of the output port, again scaled by parameter n. E1 equals n I2. So this forms the constitutive relationship for any gyrator in general terms, where potential variable of the second port is equal to n times the kinetic variable of the first port. Potential variable of the first port is related to the kinetic variable of the second port scaled by the parameter n. Now let us see how this applies to the special case of our magnetic coil. So in the case of the magnetic coil, we have a core in general, and on the core we wind a coil, copper coil. It has two terminals here, and let us say the potential across these two terminals is E. So that is equivalent to E1, the potential of the primary port or the input port. And the current flowing into the coil, I will call it as I, and that is equivalent to I1 here, the generic gyrator. And within the magnetic core, an MMF gets generated, and the MMF causes a flow of flux rate d phi by dt. So these two variables form E2 and I2. So MMF represents E2, the potential in the magnetic domain, and d phi by dt represents I2, kinetic parameter in the magnetic domain. So what are the constitutive relationships? Let us look at this. E2 is nothing but MMF here. So I will write MMF equals N is the number of turns, N into I, which is the primary side kinetic variable. Likewise, E is equal to N. I2 here represents d phi by dt. So d phi by dt. So MMF is equal to N into I, ampere turns, E is equal to N d phi by dt, again Faraday's law. So this is how electrical domain and the magnetic domain are related, and this portion is called a gyrator, or it's called the gyrator action. Now let us look at our transformer. Let me take a simple CC core. It looks like this. There is a coil on one side, I'll call that one as the primary. There is another coil on the other side, I'll call that one as the secondary. There are these terminals, 4 terminals. So let us say the number of turns on the primary coil, I'll call it as NP, and number of turns on the secondary, NS. I will call the potential across the primary terminals as EP, and the current through the primary as IP. The MMF which is generated in the primary coil, the primary in the part of the core due to the primary current flow is NP, and this will force a flux rate d phi by dt to flow through the core. Now this portion we know is a gyrator. So let me write that down here. This is a gyrator. This portion is a gyrator, and it has a parameter NP, number of turns, and there is a primary port has 2 variables, and a secondary port also having 2 variables. The power variables in the primary port is EP and IP, and the power variable in the secondary port are MP, MMF, MP, and d phi by dt. Now the same MMF is coming across the secondary coil of turns NS, and the same d phi by dt is flowing through the coil wound on the other part of the core. So if you look at the electrical part of the secondary coil, this is ES across the terminal, and the kinetic variable IS is the current flowing through the secondary coil. The same d phi by dt is flowing through this coil. Now let us represent this portion also by a gyrator Gy, and it has a parameter ns number of turns. It also has two ports, primary and secondary. The primary port in this case is in the magnetic domain, which is having same MP MMF across this also, and same d phi by dt flowing through this coil. And on the secondary side we have ES and IS. So this forms two gyrators. Now these two gyrators together form one single component called the transformer. And this equivalently I will put it as a block. It has one input or the primary port and another output or the secondary port. So for the primary port we have EP as the potential variable and IP as the current, ES as the secondary potential variable, IS as the secondary current, and the parameter is NS by NP. How does this come about? Let us take an example, relationship of EP and ES. Now let us say EP, when it passes through the gyrator, it relates to the kinetic variable in the secondary of this gyrator. So it is EP by NP. So this is equal to EP by NP, because we know EP is equal to NP d phi by dt, or d phi by dt is EP by NP, and this same d phi by dt is applied to the primary of this gyrator. When it comes out here, it links to the potential variable of the secondary, which is ES, and that is equal to whatever d phi by dt into NS. So this NS into d phi by dt is nothing but EP by NP, EP by NP. So therefore ES is equal to NS by NP into EP. So this is transformer action, and this is the transformer. This is the model that we are using in our sub-circuit. So therefore the sub-circuit contains basically these two gyrators. Now if we look at this transformer model, things will be more clear. You will see there is one gyrator, the primary gyrator, which is connected to the primary terminals NP and NP0, and these terminals are in the magnetic domain and uses the gyrator model where the number of turns N is NP, primary number of turns. Likewise the secondary side gyrator, which is secondary number of turns NS. I have introduced one more condition here for the permeance, where the core permeance is finite and it will take the value of the value of C, which is passed here. If the value of the MMF is within a particular value less than 5, or if it is greater, then it will start exponentially decaying, and it implies saturation of the core material. Now the gyrator model GY itself is given here. So this gyrator model is actually a combination of resistors, the B source. The B source in ngSpice, very powerful, where you can give expressions here, and this B source you can represent it as voltage, controlled voltage source or controlled current source. So you can go through this piece of code. This is a sub-circuit for a gyrator. Now that we have seen the model of this transformer, we are now ready to do the simulation. Before doing the simulation, one more file which we need to have a look at, this forward.car. So let me open that, this forward.car. So you see here that it is a transient analysis for 10 milliseconds. I also have a dot options statement here defining the relative tolerances between the variables and the absolute tolerances for the current and the voltage variables. I'm including the forward.net, this one which is coming from the schematic. I'm setting the background as white, foreground as black, and plotting V0 with respect to node R, looking at the inductor current and looking at VIS. Now if you look at the schematic, you will see that V0 with respect to R. You see that this is the ground potential here, but we need to see output V0 with respect to this reference node R because it is isolated. The current through the inductor IL is being seen, and the secondary current through this source is also seen, VIS. So let us have a look at the simulation. Let us go through this simulation. Let me move to the work directory, and I have all the files there, and I have typed the netlist generation syntax, gnetlist, and I am taking from forward.sch gsum schematic and putting it into forward.net. So when you run that, the netlist is generated, and now you can call ngspice forward.cir. So you will see that it starts simulating, and after the simulation is complete, it will plot the variables that we have asked to plot. We had asked to plot the output voltage V0. The one in red is the output voltage V0. You can verify by calculating according to the theory that we discussed. Another one is in blue here, IL. So the one in blue here is IL, which is the current through the inductor, and the orange one here is the current through the secondary of the forward converter transformer. So I can probably expand that for a few cycles here, zoom in, and you will see the inductor current and the current through the secondary of the transformer. Now if you look at the schematic, to look at the current through the freewheeling current, when the core flux is resetting, when you switch off this, you will see that the current freewheels in this loop. We can look at the core resetting current by looking at the current flowing through this particular zero voltage source VID. So let me plot that. Plot I VID. So you will see the currents there. I will expand it and I will zoom in for just few cycles, 1 or 2 cycles. So you will see that, yes, you will see that during this portion the switch is on, and when the switch goes off, you will see that the current in the freewheeling circuit starts flowing. So it exponentially decays towards 0. So this is the shape of the core reset current flowing in the freewheeling circuit. I will revisit this later when I am talking of the lossless flux reset and compare the two results. In this way, I will allow you to explore the various current waveforms and the node voltages of the various points of the circuit so that you totally understand the forward converter circuit. You can change the turns ratio by changing the values here and check the output results and then verify it with the theory that we have studied and try to understand and get more insight into this forward converter with lossy core flux reset circuit. Lossy because the core flux reset, when this is switched off, the current will flow in this direction through this freewheeling circuit, losing the magnetization energy in this resistor.